In this lesson, we're going to be looking at the derivative as a function. Now, previously, we considered the derivative of a function at a fixed number, so we were able to calculate our f prime of a. We said f prime of a equals the limit of f of a plus h minus f of a divided by h as h goes to 0. Now, this next equation, we're going to be looking at the derivative as a function. Now, if you remember, a function has an input and an output. So now we can put in any value for x that we choose and get an output which represents the slope of the tangent line. So now we're going to consider this a function. So graphed below is the function y equals x squared. Let's look at the value of the derivative at various points. So we're going to graph the derivative function. So let's build a table of values. So we'll have an x value, and then we're going to look for the associated f prime of x, the derivative of the function at that given x value. So I'm just going to arbitrarily choose -3. So to calculate the slope of the tangent line at -3, we're going to go back to our limits. So if we did our calculation here, we would plug -3 plus h in for our x, square it, then we'd have -9 divided by h, take the limit as h goes to 0. Now if we use direct substitution, we see we get 0 divided by 0. We're going to cancel the 9's, and then we're going to factor out an h, and the h is reduced, and then we can use direct substitution. So we get f prime of -3 equals -6. So we could actually plot this point, which represents a point on the derivative function. Let's do the same with -2. So we use our limit to calculate the slope of the tangent line, and we find we would get -4. There's another point we can plot. -1. We would get -2. We plot that point. And you should go through and verify these to make sure we're getting the correct values. So we plot this point at 0, 0. Let's choose x equals 1. We're going to find the derivative, or f prime of 1, and we would get 2. So there's another point we can plot. So let's find the slope of the tangent line when x equals 2 to this graph. Now I just want to make sure here we're looking now at calculating the slope of the tangent line to the graph at this point. And that doesn't look tangent, but we're calculating the slope of that tangent line. Now to calculate the slope of that tangent line, we're using our limiting process. So when we plug this into our limit, we would get 4. So there's another point we could plot. It happens to be a point on the graph. But the slope of the red line is 4. All right, let's find this f prime of 3. That gives us 6. So there's another point we can plot. And now we could draw a line through those points. That represents the derivative function. That's our f prime of x. Now, if we looked at finding the equation of this line, just to represent what does f prime of x equal, we could see we know this is a line, so it's y equals mx plus b. The y-intercept is 0. We could then look at the slope of the line. Notice at 0, 0, we would go up 2 over 1 to get back on the line. So here we would go up 2 and over 1 to get back on the line. This, we went up 2 here because this is 1, 2, and this is 1 on the x-axis. So we can see that the slope of the line is 2, so we get y equals 2x plus 0, or y equals 2x. The graph of f of x is shown below. Graph the derivative of f of x by plotting points. Now we found the derivative in the last slide by plotting some points and then looking at the graph, and we saw it was linear, and we were able to find the equation of the line. Now we're just going to graph the derivative function. Let's look at the graph of 1 divided by x. So we have the graph here, and let's look at the derivative of the function at different values. So I'm going to draw the derivative graph in here, have the computer do that for us. So here, there's the tangent line to the graph of 1 over x. Now we could calculate the slope of that line. We can see it's a negative slope, and it goes down 1 and over 1. So the slope of that line would be -1. So we could plot a point on the derivative graph at -1, -1. If we looked at the slope of the tangent line at other values, if we started back here and looked at the slope of the tangent line at -8, you can see it's negative slope, but it's a very small slope at -8. So we could plot a point at -8 and calculate the slope of that line, which would be a very small negative number, and we could plot that point. Looking at, let's say, x equals -1/2, which would be down in here. If I draw the tangent line there, at -1/2, the slope of the tangent line is a very negative number now. And we could calculate the slope of that tangent line and plot that point. Now let's go and look at some positive x values. Maybe x equals +1/2. If we drew the tangent line in there, again, we get a very negative slope. So when x equals 1/2, we'd have a very negative number. And as x gets larger in the positive direction, you can see the slope of the tangent lines are becoming less negative. So over here, less negative. And we notice that even if we draw the tangent line way out here, it is still a very small negative number, but it appears that the tangent line is always going to have a negative slope. So if we looked at our graph again, we saw that the slope of the tangent line at -1, x equals -1, here's where x equals -1, we said the slope of the tangent line was -1. So we would plot a point here. This would be a point on the derivative graph. So if we built the table of values, we would say f prime of x. So when x is -1, we found the slope of the tangent line to be -1. If we looked at the slope of the tangent line out here at -4, we said the slope of that tangent line, it is still negative, but it's a very small negative number. So we would be plotting a point at -4 and a very small negative value. And we could estimate that value by drawing in the slope of that tangent line and calculating, or I'm sorry, drawing in the tangent line and calculating the slope of that tangent line by looking at the graph. But it's going to be a very small negative number. And likewise, at -2, if we calculate the slope of this line, we may look at, well, it intersects the x-axis here, and it goes down 1 and over 2. So it looks like it would be approximately -1/2. So we could plot a point at -2, -1/2. And at -4, we know the slope of the tangent line was even closer to 0, so it may be around -1/4. Then as we got over in this area, slope of the tangent line, again, we would estimate we're going down 1, 2, 3, 4, and over 1. So we may say the slope of the tangent line when x equals -1/2 is approximately -4. So we would plot a point at, here's -1/2, so we'd plot a point down here at -4. So let me clean this up a little bit. So this is the process. We would look at different x values and calculate the slope of the tangent line, or estimate the slope of the tangent line, and then we'll draw a smooth curve through those points. Now as we got closer and closer to 0 from the left, you can see the tangent lines are getting very steep. So if I was to connect all of these points, we may have something that look like this. So that would be our graph, and that's not going above the x-axis because it doesn't become positive. Those are always negative. So for -infinity to 0, that would be our graph of the derivative function. Now when we looked at the slope of the tangent lines here at x equals, maybe this is 1/4, we said it's a very negative number. The slope of that line is very negative. And as we got closer to 1, we can see it's becoming less negative. And right in there, That's when x equals 1. So they're very negative numbers, but they're getting less negative. And then here at 1, it appears that that may be a slope of -1. So we'd have 1, -1. And if we looked at values, let's say x equals 3, we can see they're becoming less negative and approaching 0. So we could draw in our derivative graph that would look something like this. So that would be the graph of our derivative. Now let's go back. The program that I just used will draw in the tangent line, or the graph of the derivative function. So let's see if we can, there's the derivative, very similar to what we did when we plotted points. So the yellow graph would be our f prime of x. Oops, I went too far. The rate of inflation in the United States is a function of time. The table gives mid-year values of this function, I of t, over an 18-year period as a percent per year. Construct a table of values for the derivative of this function and graph the derivative. Now, I do have the derivative graph up there already, but how did I find, how would I have found the derivative values for, here is our I of t, and I've calculated our I prime of t. So what we could do when we're given discrete values, we know we can take the slope of the secant line. If we're trying to find the slope of the tangent line, an estimate for the slope of the tangent line at 1981, I can take the secant line between 1979 and 1981, calculate the slope of that secant line, and then take the secant line between 1981 and 1983, calculate the slope of that secant line, and average them. This is a technique we've used previously. So if we calculated the slope of the secant line through 1979 and 1981, we would have 10.3 minus 11.3, and this is a 2-year period, 79, 80, 81, so divided by 2, so we would have a -1/2. Now we're going to calculate the slope of the secant line through 1981 and 1983. So we would have 3.2 minus 10.3, and we are going to divide that by 2, and we get -3.55. Now we're going to take those two values, those are the slope of the secant lines, and we're going to average those. So we would have -3.55 divided by 2, and that gives us -2.025. And that's where this value for the slope of the tangent line came from. And notice, at 1979, we don't have a value for these a previous year, so we can't create a secant line. Therefore, I wasn't able to estimate the secant line, or I couldn't estimate the tangent line using two secant lines. Now, if we had a value at 1977, it could have been up at 15. It could have been down at -5. I don't know where it was. So I wasn't able to calculate that year, or 1997. So that's where the table of values come from for our derivative function. Now we're going to graph our derivative function. So I have plotted these points on a graph, and now I'm just going to draw a smooth curve through those points. And I'll try to get as many of those points in here as possible. Let's see if I can. Okay. So there's the graph of our derivative function. Now notice the rate of change of inflation was positive when it's above the x-axis, and the rate of change, and that's from here we can see these are the positive values here, and otherwise the values are negative below the x-axis. If f of x equals x cubed minus x, find the formula for f prime of x and graph both on the same graph. We are going to use our limits. Our definition of a derivative is the limit of f of x plus h minus f of x divided by h. We take the limit as h goes to 0. And let me just write that as a reminder. F prime of x equals the limit of f of x plus h minus f of x all divided by h. So we're plugging in x plus h for all our x's. And then we cube them. And remember, we also have to have minus, and this right here was our minus f of x. And the negative was distributed to get negative x cubed plus x. So we've plugged in our x plus h, cubed it, minus our x plus h. We notice that some of the terms cancel, so we clean that up a little bit. Now if we try direct substitution here, each term in the numerator has an h, so we'd get 0 over 0, but we could factor out an h. And now we can use direct substitution. So we get our derivative as 3x squared minus 1. Here's our derivative. That is our f prime of x, our derivative. And here's the graph of the function x cubed minus x. You can see that's the blue graph. And the derivative is 3x squared minus 1. Now there's a lot going on here with this graph. If you would do a little bit of analysis with this graph, if this is the original function here, now look at the slope of the tangent lines. Very positive through here. That's why the graph of the derivative is very positive there. Notice the slope of the tangent line is 0 there. We have the derivative graph is 0. Slope of the tangent line, 0. So our derivative graph is 0 there. And between those 2 points, the slope of the tangent lines would be negative. and that's why the derivative graph is in the negative area. And then the slope of the tangent lines here, positive, that's why the derivative graph is in the positive area. Another example. Find the derivative of the square root of x minus 1 and state the domain of f prime. We're using our definition of a derivative using a limit. This particular problem we need to multiply by the conjugate. When we multiply the conjugates together, and we notice that we can cancel some like terms with opposite signs. And now we can use direct substitution. So we get f prime of x equals 1 divided by 2 times the square root of x minus 1. You should be able to go through this process on your own. Now it says state the domain of f prime. In the denominator we have a square root of x minus 1. We know that the square root cannot have a negative number or 0. So we would have to have x minus 1 has to be greater than 0. So x would have to be greater than 1. Now notice, the domain of our original function, f of x, is x is greater than or equal to 0. A function and its derivative can differ in its domain sometimes by one value, usually at an endpoint. And if we graphed the derivative and the function and its derivative, you should be able to tell which one's the function. The yellow graph is our square root of x minus 1, and then the blue graph is our derivative. And do the analysis. Just look at where the slope of the tangent lines for the f of x function would be positive, where it would be negative. Now, I said where it would be negative. Is this ever negative? Well, you'd say no. The derivative graph is blue, and it's always above the x-axis, which means it's always positive. Find the derivative, or f prime, if f of x equals 1 minus x divided by 2 plus x. We're going to use our definition of a derivative. And again, we're plugging in x plus h to 1 minus x divided by 2 plus x minus our f of x, all divided by h. Here we got a common denominator in the numerator and then invert and multiplied. So just to clear up that step a little bit, we would have to multiply, to get a common denominator in the numerator, we'd have to multiply by 2 plus x divided by 2 plus x here, and then 2 plus x plus h divided by 2 plus x plus h. That would give us our common denominator, and you can see those quantities down here, 2 plus x, then our 1 minus x minus h here, and then this quantity is here, and our 2 plus x plus h is here. And then we have our common denominator right here, but then we invert and multiply the h over 1, and that ends up in the denominator. And again, go through this, make sure you understand all the algebra for this. Okay, we're going to simplify it further, canceling out our like terms in the numerator, and we can see the h will reduce, and we're left with this. There's the derivative of our f of x. And you should be able to identify which one is the derivative graph and which one is the graph of f of x. Let's look at some other notation that represents the derivative of a function. All of these represent the derivative of a function. You can see it written any one of these ways. Now, typically in our class, we will see these three ways most frequently, and we'll see this sometimes also. But typically, we won't write the derivative like this. I've seen this in a lot of the business calculus books, but typically we'll use these first three. This one's called Leibniz notation. We'll see that quite frequently. So there's our Leibniz notation. A definition. A function f is differentiable at a if f prime of a exists. It is differentiable on an open interval ab if it is differentiable at every number in the interval. So that word differentiable means we can find the derivative at a particular point. It's differentiable. Where is this function differentiable? This is the absolute value, and I've put the graph up there for us. Now, if we look on the interval from negative infinity to 0, not including 0, we'd say, well, that's a line. It's continuous. It appears it would be differentiable there, as well as from 0 to infinity. The only place that we may want to check is at 0. Is it differentiable when it comes down to that corner? Well, how would we determine if it's differentiable? Let's use the definition of a derivative, which is the limit. Now for this one, I'm going to use the alternate notation, f of x minus f of a, all divided by x minus a as x approaches a. Now let's plug in our f of x. So f of x is the absolute value of x, and we're trying to determine if this is differentiable at 0. So that would be minus 0 all over x minus 0 as x approaches 0, which simplifies to the limit of the absolute value of x divided by x as x approaches 0. If we looked at graphing y equals the absolute value of x divided by x, we would get a clear indication of what's going on. We could also build a piecewise function for this. We know that a piecewise function, we have f of x. As a piecewise function, we would have positive x over x when x is greater than 0. I didn't want that equal to sign. Or negative x divided by x when x is less than 0. Now, if we analyze this limit here, using our one-sided limits, we could see as we would take the limit of our f of x as x approaches 0 from the right, That's going to be positive 1, but the limit of f of x as x approaches 0 from the left, that's going to equal negative 1. So this limit does not exist. Well, what did we just show? We just showed that since that limit does not exist, f prime of x does not exist at 0. So it is not differentiable at x equals 0. I believe I have a graph here of the absolute value of x divided by x. So let's just look at that and verify. Let me get a little room here for that. So there you can see the graph. It approaches positive 1 as x approaches 0 from the right, and negative 1 as x approaches 0 from the left. An important theorem: if f is differentiable at a, then f is continuous at a. So if we can differentiate a function at a particular point, we know it is continuous at that point. Notice this is a conditional statement, an if-then statement. It does not say if and only if. You need to be careful. We cannot switch the hypothesis and conclusion and it's still true. We can't say if a function is continuous at a, then it is differentiable at a. And if you just think about the last example we did, the absolute value graph, you could show that this is continuous at a when x equals 0. We could go through the 3 criteria and show this is continuous at x equals 0. However, it was not differentiable. So this is not an if and only if statement. We only can say if f is differentiable at a, then f is continuous at a. We cannot say that if it's continuous at a, then it is differentiable. So be very careful with that. How can a function fail to be differentiable? Well, let's look at 3 ways that a function may not be differentiable. First is if we have a corner or a cusp. We just saw that if we have a corner with the absolute value graph, so if we had something like this, it's not differentiable where that corner occurs. So it would not be differentiable at x equals a. That's a corner. Now a cusp is something that looks like a wave or a shark fin. So this would not be differentiable at that point. You can see it comes to a point again, so it's not differentiable. That's called a cusp. So those are 2 different ways that a function would not be differentiable. Another way, whenever the function is discontinuous. So if we had a function that looked like this, that's discontinuous at x equals a, therefore it is not differentiable at a. Now it is differentiable all the way up to a, but it is not differentiable, and differentiable here, but not at a. And if we had an asymptote, it wouldn't be differentiable at that point. Whenever there is a vertical tangent, so if we have a graph that looks like, let's say, this. If we looked at the tangent line right here, that tangent line would be vertical. Therefore, it's not differentiable at that point.